In terms of emissions, one of the ways we can reduce emissions associated with the plastic supply chain is by bringing in more biogenic carbon, more bio-based feedstocks.
Welcome to Science with a Twist, a podcast for curious people who enjoy exploring how science impacts our daily lives. From technology that helps the fight against COVID-19 to solutions that help clean the water we drink, it's all thanks to science. In each episode, members of Thermo Fisher's scientific team talk to experts who are on the cutting edge of redefining how we exist. Let's get started.
Hello, and welcome back to Science with a Twist, brought to you by Thermo Fisher Scientific, the world leader in serving science. I'm your host, Terri Somers. Today's episode will delve into the critical issue of plastic waste and pollution. We will explore the crucial role that the scientific research community, as well as the biotech and biopharmaceutical industries, can play in mitigating plastic waste and building a more sustainable future. There's no denying that plastics make life easier, and plastics are everywhere, from disposable water bottles to food storage to life-saving medical supplies and equipment used in research. Unfortunately, plastic pollution is gravely harming our planet. There are approximately 350 million metric tons of plastic waste produced worldwide annually. Roughly 8 to 10 million metric tons of plastic end up in our oceans, accounting for 80% of all marine pollution. The need for change is dire, and scientists around the world are urging immediate action. Recognizing the need to address plastic pollution, Earth Day's 2024 theme, Planet versus Plastics, is clear, and it encourages a significant reduction in plastic production by 2040. To support that effort and other global initiatives, many industries are implementing more sustainable processes when it comes to plastics. For life science researchers and the biotech and biopharmaceutical industries, this poses a unique challenge: the need to balance the life-saving nature of plastics used in healthcare and research with protecting the environment. However, progress is still possible within the life science industry thanks to outside-the-box thinking and innovative solutions. In today's episode, we're pleased to welcome Kat Knauer, Ph.D., Senior Researcher at the National Renewable Energy Laboratory and Chief Technology Officer of the BOTTLE Consortium. In her current role, Kat is developing sustainable technologies to chemically upcycle today's existing plastic waste streams and develop new plastics for the future that are recyclable by design. She's a polymer scientist with a Ph.D. in polymer science and engineering from the University of Southern Mississippi. She's dedicated her scientific career to solving the plastic waste problem, and we can't wait to hear her insights. Today with Kat, we'll discuss the importance of reducing plastic waste and the role that life science organizations can play in building a cleaner, more sustainable future. Welcome, Kat. Thank you so much for joining us.
Yeah, happy to be here. Thanks, Terri, for having me.
To start, we'd love to hear more about your background and your current focus with the National Renewable Energy Laboratory.
Yeah, definitely. Happy to shed some light about what we're doing at NREL. So NREL is what we call the National Renewable Energy Laboratory. We're based in Golden, Colorado, and I act as a senior researcher here and under the umbrella of what we call the BOTTLE Consortium. So being a government lab, we love our acronyms. So BOTTLE actually stands for Bio-Optimized Technologies to Keep Thermoplastics Out of Landfills and the Environment. We thought we were quite clever at the time when we came up with this. However, it's confused some people into thinking that we only work on plastic bottles. And in reality, the BOTTLE Consortium is focused on addressing the waste challenge across the entire plastic supply chain. So from single-use plastic that we typically use, say, in the R&D space or in consumer packaging, to textiles and fibers, to electronic waste, all the way up to things like high-performance materials and thermosets. So BOTTLE is based out of NREL, but we're actually a consortium of 8 national labs and universities across the United States, all bringing in a very specific skill set to address this challenge because it is very multidisciplinary. It's not just a polymer science challenge. It's a social science challenge. It's a biology challenge, chemical engineering, process engineering. And so we have a great skill set of folks all in BOTTLE working on this. And we have 2 kind of main pillars and main drives, both within my research at NREL and the entire BOTTLE Consortium. The first one being, how do we effectively manage the plastic waste that we're dealing with today? How do we bring those carbons back into circulation and move away from the take, make, waste economy that we've created to a circular economy where we can reuse carbons in an infinite cycle. And then the second big push or big pillar is all focused on going back to that drawing board and kind of turning off the problem at the faucet. How do we redesign plastics to be more intrinsically recyclable by design, as well as more biocompatible and compatible with our natural environment and ecosystem? And so those are our two big pushes at NREL within my own team and within the Bottle Consortium and what we work on.
Well, what piqued your interest in the study of plastics? Was there a light bulb moment where you realized how critical this issue was for the environment?
Yes, I was lucky enough, young in my research career, to kind of have that aha moment. And for me, this started at the undergraduate stage. So I did my undergraduate degree in chemical engineering at Florida State University. And while I was there, they opened up a new research facility that was all focused on polymeric materials and other types of material science research. And they were hiring undergrads to come work there, and I needed a job, I needed money, I liked science, so I went to work in these labs, and that's where I learned what a polymer was for the first time. And it's when I learned polymer chemistry, and also where I learned about how fascinating and amazing these materials were and how much I enjoyed polymer chemistry and how integral it had become to quality of life and our society. But it's also where I put two and two together, of course, and realizing that the primary component of plastics are polymers. And this wonder material, this amazing science has also led to this huge environmental crisis that we're dealing with today. And as a scientist myself, that kind of sparked my interest into, well, how do I show society that these materials can be sustainable, that we don't want to move to a world without plastics because that's going to be a worse world. But how do we responsibly manage these carbons? And how do we rethink the way the plastic supply chain works? And so that promoted or inspired me to pursue a PhD specifically in polymer science, hoping that if I became a quote expert in this, maybe people would start listening to me. And the more I learned about polymers, the more I could help solve this problem. And so that was kind of my aha moment in undergrad, is really tying the two things of really cool chemistry with also an environmental crisis and trying to bridge the gap in between and solve this problem.
Mhm. Well, not all plastics are created equal. So, what are the different types of plastics and how do they differ in terms of sustainability?
Yeah, so if you handle any piece of plastic on a regular basis, and especially in packaging, you look underneath and they have those chasing arrows with a number in between. So those numbers correspond to the type of polymer that is in that plastic. So one, being one of our more ubiquitous ones, stands for PET, polyethylene terephthalate. This is an aromatic polyester. Then we move into the other 1 through 7 plastics, and we move into what's called polyolefins. So polyolefins are, even those, not created equal. We have multiple types of polyolefins. We have polyethylene, which is just a typical carbon-carbon backbone. Then we have polypropylene, which is the repeating unit of propylene. Then we have polystyrene, which is the repeating unit of styrene with an aromatic styrene monomer linker. And each of these materials that we're dealing with bring a very specific property to the table. They do very well in the application spaces they were designed for, but they're completely incompatible with each other, very different chemistries. And then as we move down the 1 through 7, it becomes even more complex. So up the 1 through 7, you're dealing with mostly polyolefins as well as some polyesters, and then PVC, which is polyvinyl chloride. And then once you get into the number 7 plastics, that's when you then enter the realm of even more complexity. So that's when we see things like nylons, which are polyamides, polyurethanes, polycarbonates. Polycarbonates are going to be things you see in like credit cards and CDs and Nalgene bottles. And so it's an incredibly complex space that has had beautiful, meticulous chemistry design to make these materials designed for those applications. But because of that, we now have a very heterogeneous waste stream that we're struggling to recycle and manage on a daily basis because of that complex heterogeneity that's built in to these different types of plastics.
So, is it the more complex plastic they are, the less sustainable, or the more difficult they are to make sustainable, to break down?
I would actually say it depends, because in some cases, as you bring in a heteroatom, so you bring in an ester linkage or an amide linkage, you're actually bringing in a chemical handle that makes it easier to deconstruct that plastic back to its original building blocks. So that could bring in some benefit and motivation to make a more complex backbone. If you think about polyethylene, which is nothing but a carbon-carbon backbone, that seems very, very simple, should be easy to manage. But the fact of the matter is, polyethylene is incredibly difficult to depolymerize and deconstruct back to ethylene, the original building block, because carbon-carbon backbones were designed to be very robust and not depolymerize back to monomer. And if you look at something like a nylon with an amide bond, that's when you think, well, maybe this is more complex. But if you think about deconstructing back to original building blocks, it's easier to do so with a polymer like that. So there's this weird balance of looking at the chemistry and seeing something that looks more complex, but could actually be easier to deconstruct. And then when you think about polyesters, there's a lot of different types of polyesters out there. And it looks quite complex as well. But many polyesters that we're designing today are designed to be more compatible with biological systems and have pathways of enzymatic and microbial degradation so that these materials can biodegrade in multiple types of environments and composting facilities. So it's really tough to say flat out that complexity and structure leads to less sustainability or more unrecyclable, because it's a balance that we're still playing with that we haven't totally figured out yet in terms of how do we make something more, quote, recyclable or sustainable.
Well, bio-based plastics seems like a particular area that would be interesting. Can you talk more about these and where you see them having the greatest impact?
Yes, definitely. So a bio-based plastic essentially means that the feedstocks or the building blocks used to make that plastic came from a biological feedstock. And this could be many things. Historically, this is typically going to be sugar-rich crops. So things like corn, sugarcane, beets. These types of crops are converted into sugars that are then converted into monomeric building blocks that can be used to synthesize plastics that we use today. So that's what a bio-based plastic is. And sometimes it's confusing because when people hear the terminology bioplastic, they tend to think that that is all the quote compostable materials on the market today. But in reality, a lot of our compostable plastics are still coming from fossil-based feedstocks and not from biological feedstocks. PLA is one that is an example of a bio-based polymer. So this is polylactic acid, and it comes from mostly corn-based feedstocks that are converted into sugars and through a fermentation process used to make lactide and used to make PLA. So that's a great example of a true bio-based plastic on the market today. This is something that is near and dear to me. One, because at my core, I'm still a polymer chemist. So I want to make new polymers, even though I spend a lot of time taking them apart now. But bioplastics are emerging. Well, not necessarily emerging. They've been around for a long time, but they're gaining a lot more traction now than they ever have before. And this is for a few reasons. One, when we look at life cycle assessment studies, so LCAs, that's when we look at the life cycle impact of a piece of plastic from the production all the way to the end of life. We have found that in terms of emissions, which being the Renewable Energy Lab, we think about everything in terms of climate change and emissions reduction. So in terms of emissions, one of the ways we can reduce emissions associated with the plastic supply chain is by bringing in more biogenic carbon, more bio-based feedstocks. Those are carbon sequestering feedstocks, and they're going to help us bring down our life cycle emissions of making plastics. So that's one big plus. The other cool part about bioplastics is that not all of them, but some of them have also been designed to break down in industrial or home composting facilities. So it brings in another end of life option beyond landfill. However, our same LCA studies, both in the literature and ones we're doing ourselves, have shown that to really get to net zero emissions for the plastic supply chain, it's a combination of high utilization of bio-based content plus high recycling rates. Composting plastics is not going to get us there. We need a better recycling infrastructure. And I think that's what's lost sometimes in the communication around bioplastics. People think, okay, this is all for composting. But in reality, we want to keep those carbons circular too. Biogenic carbon is just as valuable and it should stay just as circular as fossil based carbon. And so, what we're really pushing for now is yes, let's adopt more bioplastics into our supply chain. We need more bio based feedstock, but we have to fix the recycling problem at the same time. We need higher recycling rates to do so. So that's what our team focuses a lot on in our group is in the recyclable by design piece, designing new bio-based plastics, but designing them for recyclability.
Okay, very interesting. Recycle, recycle, recycle.
Yes.
Single-use plastics, they're commonly used in the life science research and in biotech and biopharma. Can plastic waste be eliminated completely in the lab, or is reduction and improving recyclability really the goal?
This is such an important question, and I am so thrilled to be discussing this with you guys today because it's one that's often overlooked when we do discuss the recycling industry and how we grow the recycling industry. Is we don't necessarily always think about laboratory R&D and medical waste streams that use a ton of single-use plastics. And to answer your initial question, no, I do not think the future of R&D and life science and medical research is eliminating plastics. We're simply not equipped to do so. And I also think that will be incredibly prohibitive to innovation and growth in research in the future if such measures were put into place. I mean, even just thinking about the medical field in general, which I know is different from R&D, I mean, the way we can sterilize single-use packaging, the way we sterilize polyethylene packaging with gamma radiation has significantly reduced hospital-acquired infectious diseases, and moving away from that is not a good idea. But we also rely on single-use plastic in the lab space to have security and faith in our data, highly repeatable results. And so I don't think elimination is the key here. I think it's reduction and reuse. Those are always the two most important R's, in my personal opinion, is reduction, reuse first. And so some examples of really great innovations I'm seeing come out in this space that we're excited about is new instrumentations and setups to reuse chips and wash tips. We have a great collaboration in place where we've just installed one of their tip washing instruments, brand new for us. So our lab and our team are trying this out for the first time. But what we're really excited about is we're trying to calculate how many tips we are going to be saving through washing and then using a life cycle assessment tool, actually calculate the emissions impact we're having by reusing tips. So that's one exciting story I wanted to tell you guys. But in general, I think moving towards more reduction and reuse principles in the laboratory space, it's going to be painful. There's going to be growing pains in the beginning. There's going to be some things that don't work. But I really hope to see more labs push for this and bring in more programs such as tip washing, glove recycling, other types of reuse mechanisms to reduce their impact in terms of single-use waste.
Looking ahead, what do you envision for the future of plastics?
This question is always one that stumps me a little bit because I have to wear my NREL hat or my personal Kat Knauer hat when I answer this question. But the future of plastics, my ideal optimist part of me is one that is going to be more circular. What I hope to see the future of plastic is I want to see less reliance on fossil fuels, less virgin production, and a waste-based system for plastic manufacturing. And not just through recycling, but also through biomass utilization. So I see a future where we move away from these silos of fossil fuels and biomass, bio and chemistry, and see more of these systems integrate together. And I want to see refinery plants and plastic production plants have a system where waste carbons are coming from recycled plastics, waste carbons are coming from biomass, combined together to have a waste-based system. And we have a circular process set up for carbon that's no longer reliant on both agriculture or fossil fuels. And this is going to be really tough to do for many, many reasons. But one of the hardest parts is access to recycling infrastructure. We simply do not have enough curbside collection. Even in the US alone, only 30 million Americans have access to curbside collection of our entire population. I mean, that's wild to think about. And so The future of plastics is one where I think plastic producers invest in municipal waste collection to get those plastics back because they see it as valuable. And ideally, they all come back for recycling, and we have, again, that circular carbon system for plastics. I also hope to see the future of plastics be one that moves away from single use and towards long term durability. And I think that that is a trend we're already seeing start to happen. The trends of reuse, bringing your own reusable bags and silverware and cups, and also framing plastics as something that are valuable. They're not designed to be single use and disposed of in the same year they're produced. They're valuable materials that we should be keeping for long periods of time. So that's what I think the future of plastics is.
Well, you've talked about integration and you've kind of touched a little bit on collaboration. So, how important would you say collaboration is for reducing plastic production and achieving a more sustainable future? And are there any collaborative initiatives out there that you'd like to highlight?
Yes, it's essential. I mean, I think we all are in agreement, no matter what we disagree on in terms of the next steps for plastics. One thing I think the entire world agrees on is collaboration. It's not a polymer producer problem. It's not a consumer problem. It's not a waste collection problem. It's everybody's cohesive problem. And so we need the brands to be communicating with the converters, to be communicating with the polymer producers, with the monomer producers, and we need a better education system for consumers. There is so much of a gap between when that plastic leaves a plant and enters the consumer's hand. That disconnect is so extreme. And that's one of the reasons we have this problem with logistics and waste collection is that consumers are so confused as to how to recycle properly and where things go. And so I think collaborations across NGOs, governments, municipalities, and the entire scientific community and the life science and R&D and medical community, it's tough to bridge all those gaps. We're, a society where we operate in silos when it comes to these technologies. But I am hoping to see these collaborations merge over time. And some exciting collaborations, that I've been able to experience in my career in Bottle and at NREL that I'm particularly excited about. One I will mention is with Amazon. So Amazon approached us a few years ago. They had an idea about redesigning their mailers and their packaging system to be bio-based, getting to that net zero emissions economy by using bio-based feedstocks. But recognizing that our society doesn't currently recycle bioplastics, we had this idea of working with Amazon to do a reverse logistics approach and to design a recycling system for bioplastics first, implementing that into a society through a spin-off company that we're now spinning out of our labs, and then going back and starting to redesign packaging to bring in more bioplastics now that we know there's a recycling pathway for them. So this really exciting collaboration we've had with Amazon for the last 2.5, 3 years has led to a spinoff that one of the postdocs in our group is starting a company called Esther Cycle. So that's my little plug for them. Another exciting collaboration we have has been with Patagonia for the last couple of years. Patagonia has been a wonderful advocate for climate and sustainability. I think they're kind of the star child of that. They talk the talk and walk the walk. And for a long time, they've been taking back used clothing that's no longer really usable with the intent of wanting to recycle it. And they've been storing this and looking for recycling solutions, but there's not a lot of options for textile recycling. And so working with Patagonia and their partners, as well as with Borreo, which is a company down in South America that's doing fishing net collections, we're trying to bring in this integrated system of both collections, brand, and recycling and develop a better textile recycling system for these valuable fibers. This has also led to a spin out of our group called Terraform, which is a really exciting company that's trying to scale up a mixed textile recycling platform. So obviously I'm biased. These are collaborations I've been lucky enough to be a part of, but I think they're really great examples of how powerful some of these can be. And also the investment that these big brands are making into these topics because they need more sustainable solutions as well.
Those sound like great collaborations and promising new companies that are being formed as a result of those collaborations. For our listeners, what can we do as individuals to help reduce plastic waste?
I think what we talked about already, Terry, the two most important R's are always going to be reduce and reuse. So thinking about your own decisions at home and moving away from convenience, which is very difficult to do. Single-use plastic has made us addicted to convenience, and changing habits as human beings, we all know, is inherently very difficult. So taking small steps to reduce your single-use plastic usage is critical. That's step one. Thinking about how you order takeout, or even when you're at the grocery store and you're looking between two products, one is a little bit more overpackaged, the other one is less packaged and is more recyclable packaging. Maybe choose that one. And that's not always easy to do. We unfortunately live in a society where making sustainable and green choices is still very privileged. It is typically more expensive to make those choices. Hopefully, over time, this will become more accommodating to others and get better. But these are some things I would consider taking action on. Another very important thing for listeners to do that I cannot stress enough is to try to educate yourself on what your local municipality collects in curbside recycling. All that material goes to what's called a MRF, a material recovery facility. And these facilities work very hard to get recyclables out of your mixed bins. And it is a dirty and hard job. So the better we do at making sure we're putting the right material in there, the easier it's going to be for them. It's going to make them more money. The economics around recycling will improve, and overall, we'll get a better system in place. But that all, unfortunately, still comes down to us at home as consumers to do it correctly. And so I really want to tell everyone to please try to find out in your local municipality how to recycle properly. Educate yourself, get involved, call them up, ask them questions. They want to help you guys too. So I'll leave it there. That's my PSA and my call to action.
That's a great call to action for us as individuals. But what about the industry at large? Is there a call to action that you would like to propose?
I think the industry at large is somewhat similar. I mentioned this earlier in the podcast that there's going to be growing pains in the R&D and life sciences and research space when we try to transition to reduction and reuse. It is not going to be smooth and it's not going to be easy. But taking baby steps and trying things slowly, that would be my big call to action for the life sciences and the research community. Trying things one at a time. Don't go for it all at once. Don't go to your laboratory and say, okay, we're going to try reusing everything. We're going to install all these new tip washers, everything all at once. Take baby steps and try things, make them better, report your data, and take something and metrics over time to show, how does this look? Is this working for us? And so that would be my call to action for groups is take baby steps, try things out, pilot it with your team, get feedback from your team, and then share with others what you learn. And that's, I think, how we're all going to get to less waste and more sustainable lab culture.
Dr. Kat Knauer, this has been really enlightening. Thank you so much for joining us today and for sharing your expertise on such a crucial topic.
It's been my pleasure. This has been so much fun, and I am very, very happy for the opportunity and so glad to celebrate Earth Day with you guys on this incredibly important topic that's so near and dear to me. So thank you very much for having me.
Thank you for listening to Science with a Twist. Please join us next time.
Thanks for tuning in to this episode of Science with a Twist. This show is brought to you by Thermo Fisher Scientific, the world leader in serving science. If you enjoyed this episode, then follow Science with a Twist wherever you get your favorite podcasts.